Hi, everybody. Professor Ghassemi here. Welcome back to another lecture on AI agents at Michigan State University. The topic of today's lecture is on agentic design patterns. Specifically, there's three topics I'll be taking you through today. The first is a motivation. So why should you care to learn about these design patterns? The second is a survey of some of the essential design patterns that we're seeing used today across common applications. And the third are some of the emerging tools and methods, things that you'll probably want to be aware of if you are a researcher or interested in creating innovations in this space. Let's start with the motivation. So first and foremost, recall that an AI agent is a system that integrates three things. There's a generative AI system, that's typically a large language model. And then there are a set of tools, things like web search, as well as memories. Think of a database as an example. And it's the interface of these three and the interaction with an external environment, be it a user or some other ecosystem, that creates the AI agent. In order to leverage these three items, the LLM, the tools, and the memory, to achieve a goal within this environment, the best possible response or some other optimization, there's three things that the agent does. The first is perception, trying to figure out what actually matters from that input, and importantly, if anything was missing. There's planning, which is figuring out what it wants to achieve, how does it measure the progress, and what specific steps does it take. And in order to do this planning, this is where it leverages the tools and the memory. The tools here are the things it can use to help it as it plans its specific steps. And the memories are prior information that's relevant or important as it wants to plan those specific steps to achieve the goal. Finally, of course, the last action is to take the action, generate the output that will change the environment over here toward the goal. So to help us develop a more intuitive understanding of what these key components are, I think it helps to ground it in a couple of examples. Let's start with ChatGPT. So in the case of a commercial language model like ChatGPT, you, the user, are the environment. You provide inputs in the form of prompts, and those prompts could be text, they could be images plus text, or they could even be your voice. And when you provide those inputs, what's important to understand about this perceptual process is, at least as far as I know in 2025, ChatGPT is only really concerned with the text and the images you provide. So I'll give you an example. If you use the voice capability on your ChatGPT app, on your phone or on your machine, and you speak to it, and you ask it a question in a sarcastic tone versus a regular tone, you don't get a difference in the response type. And the reason is because what is being perceived, the perceptual part of ChatGPT, is focused primarily on the text content and the images. It's not really paying attention to how you say things, it's paying attention to what you say. Okay, so this is a real example of that perceptual process of the agent in play. It's trying to figure out what from the input to pay attention to so that it can perform its objectives as an agent. After this perception is completed, it's provided to a large language model, which has access to some tools and some memories. The tools here, let's say, are web search, and the memories here are some things that it's remembered about you in the past. If you have used a commercial LLM such as ChatGPT for any period of time, you've probably noticed that at the bottom of your chat, every once in a while, you'll get a message that says updating memories. And this is when the LLM decides that there's something about what you revealed to it in the course of the prompt that's worth remembering about you, your profession, your age, where you live. It might be a set of things that are considered of interesting or relevant if it wants to generate prospectively some responses about you. Okay, but this LLM, using a combination of what it perceived and knowing what the tools and memories that are available are, goes through a planning process. Okay, this could use chain of thought. like we discussed in our previous lecture, or some other method. And a typical planning process might be to determine if we need to recall certain memories based on what the input was, determine if we need to call any tools like, hey, did the user ask me a question that's going to require a web search? Did they ask me to choose a good restaurant for them as an example, in which case I'd need to look up restaurants in their area, maybe recalling where they live. I'd need to do that web search and then, of course, synthesize the results so that I can respond to the user. Okay, so as you can see here, an AI agent like ChatGPT integrates the generative AI, the tools, the memories to make sure it can action the environment through certain subcomponents of the input that it perceives. It achieves that through planning. So let's go through a second example here that's probably a lot less familiar to many of you, which is an AI agent in the context of health. So here, the environment is no longer a user who's prompting the system, but the environment is the patient. So this patient, instead of providing words or prompts, is providing another kind of input. It's providing labs, vitals, imaging, and other information about the state of their health. And just like in ChatGPT's case, there is a perceptual process that was taking a subset of what you provided it. Remember, we were ignoring some of the properties of the voice and just we were only interested in the text of what the user said. Well, so to here, this AI agent might only be interested in a subset of the data that comes from the patient. Let's say it's the labs, the vitals, and the imaging. Now, once it collects this data, this LLM wants to use a combination of what it collected, along with some tools and some memory, so that it can perform planning and generate an action that will ultimately help advance the state of the patient. Let's say the goal here is survival. I would certainly hope that that's what a health agent would want to achieve. So some tools in this case you could see may not be something as broad as a standard web search, but maybe it's a search of very specific scientific publications from a known authority like PubMed. Or maybe it's a tool that can take the images that are passed in and turn those into a text report of any anomalies that were seen in the image, an issue in your brain scan, something weird in your CT scan, and so on. So you might call a tool like VisAI that takes those images and turns it into text so that this LLM can reason on it. Memory in this context might be elements from the medical history. Do you have allergies that were recorded from a previous visit? Do you or your family members have a history of cancer or other ailments? And so you can see here that there's a pattern here, right? That's similar between what ChatGPT does and what this AI agent do. There's a perception of certain elements from the environment. There's a generative AI system, an LLM, that's choosing to use some tools and pull from some memories. It uses a combination of the tools and the memories to form a plan. Is the patient stable? Is the diagnostic known? Should I order tests? Should I apply medication? So that ultimately it can create a action. In this case, what should I do to help the patient survive? So there's a clear parallel here, right? Both systems are performing perception planning to generate actions, and the way they're doing that is with a generative AI system, as well as some tools and some memories. The challenge here is that the proper design of an AI agent depends on the task. And just to give you an example here, let's say that this AI agent, despite having these tools and the memories and having carefully generated its plan, makes a mistake. That happens, right? If you've used an LLM, sometimes they lie, sometimes they err. And what you would not like to happen is for an action in the context of a patient being taken care of is wrong, because that error could be fatal. You could really harm someone if you make this mistake. And similarly, it might not be the case when you're pulling data from this authoritative source that all of the content within that authoritative source are held equal. Some papers that get published academically are higher quality. Others are, maybe not low quality, but let's say the quality is less high than others. And so there might be some things about the system, given how consequential the outcome here is for this patient, that make this design pattern of performing the perception, letting the LLM use tools and memory to generate an action and applying that action to the patient, that design pattern could be problematic. So what's the solution here? Well, one thing we could do is take the actions that are coming out of this agent and we could pass them by a doctor, a human expert who can vet, yeah, you know what, that action applied to the patient makes sense, or no, I want to decline it and come up with something else. And that would solve the problem of just passing these actions through automatically in a loop. This is an example of a human in the loop design pattern, because as you can see within the loop, we have a human here that's doing a validation. And the design patterns that we will be covering later in this lecture are basically different generalized solutions that help solve common classes of problems. This is one example, right? You have a problem where making a mistake is highly consequential. How you solve that problem is by putting a human in the loop. So now that we've covered the motivation for these agent design patterns, let's go through a survey of some of the essential patterns that are out there, starting with the simplest one, which is the single agent pattern. This is the one you all know and love. It's the super basic interaction pattern that you have with ChatGPT when you're calling the API. You pass in an input. This could be a prompt that you have, and you specify in this agent a system prompt. It could be, for example, performing sentiment analysis on some text. And you just call the agent with some text you want to perform the sentiment analysis on, and it responds in a way that you have specified per the system prompt. Advantages of this are it's very easy to implement, and it's highly predictable if you've engineered your prompts correctly. The limitation, of course, is that you can't handle multi-step tasks, and every time you want to achieve a new task with this agent, you're going to have to either change the system prompt or create a new agent with a different system prompt. So it's a little rigid. For the sake of clarity, a system prompt in the case of the sentiment analysis agent might look something like what you're seeing on the right-hand side here. So we would specify that the task is to classify input text, and we list some of the classes we're interested in. These are the usual suspects: positive, negative, neutral, and mixed. We might also indicate how we want the answer format to look in the response. Sentiment followed by colon and one of the four options we have up here. So when a user provides an input, the perceptual mechanism captures this input. Lauren loves her camera. And the agent uses the system prompt plus the input to generate an output, positive. Super simple. It's what you're used to. What distinguishes this from the chain of thought pattern is that the agent in this case is decomposing the problem into a sequence of reasoning steps. And at each of these reasoning steps, it's making, in most instances, but not all, a call to a LLM that handles that part of the reasoning. Okay? So we'll go through an example in a minute, but at the highest level, this is useful for step-by-step problem-solving tasks, math, logic, and so on. And that's because this setup allows you, through decomposing the problem instead of handling it in one system prompt, it allows you to do multi-step reasoning that is easier to debug and therefore easier to fix as you're doing the prompt or agent design, which is usually actually a little bit harder in the chain of thought pattern than it is in a standard system prompt. Okay, it's also a little bit slower for obvious reasons. If I'm calling an LLM 3 times because I've decomposed my problem into 3 steps, that's obviously going to take more time than if I call it once. Let's look through a real example so that you have an intuition for functionally how this chain of thought pattern is implemented. So let's say I have a user input, very simple. I have 2 cows, Mary has 2 sheep. How many animals do we have? And then I've designed a chain of thought system prompt here, which is you are an agentic chain of thought reasoner, and you work in these 4 phases that I have specified, by the way. You could put something else for your reasoning pattern. You plan, you solve, you critique, and then you finalize. And you always output the most appropriate phase and then the content for that phase. Okay, so that's the input and the system prompt. So the first thing that you do is you would call this agent with your input, right? This is exactly what was specified above. And given this input and the system prompt that the LLM has, it should provide an output where it gives you the phase, in this case, planning, which was the first step. Remember up here? Look, first step was planning. So it will output plan. And the content that it will output are some steps. I'm going to count cows, I'm going to count sheep, and then I'm going to add them. And it will then go and make a second call to an LLM, independent of the first one. And this time, notice what it does. It passes both the task as well as the plan. This is the same plan that was output from the first step, right? See, count cows, count sheep, add them. So this gets input into the LLM with the task and the plan, and the same system prompt. What comes after plan? Well, according to our system prompt, the next step was solve. And so it looks at these 2 and uses this to generate the solve. In this case, the results are the cows are equal to 2, the count of the sheep is equal to 2, and add them results in 4. Okay, and so it gives a candidate answer to this question up here as 4. What's really important for me to note here is that in the system prompt, you may have noticed I didn't specify to make the steps in this particular format. That was something the LLM came up with on its own. You could, of course, specify that format with more clarity, or you could leave it up to the LLM. Usually specifying makes the performance more predictable, and so I therefore recommend it. Okay, so anyway, though, we passed in the task and the plan into the second step. We got the solve. Okay, so this ends up coming up into our list for the third call to the LLM, which is the critique phase. So it takes these 3, it generates a critique. So it looks at what were the steps. You wanted to count the cows, you wanted to count the sheep, you wanted to add them. And it's supposed to look at this input and basically criticize if this makes sense or not. In this case, the verdict that the LLM gave was pass. So this comes up now into the input to the next step. And if you recall, the last step after the critique phase was the finalization phase. So in this case, this input comes into the LLM and the output is answer is 4. The justification is provided down here. And this answer is what you would pass back to the user in the chain of thought pattern. Okay. So I wanted to break down this example so that you understood in a chain of thought pattern, particularly when you're dealing with an agentic treatment of the problem, as opposed to just regular prompt engineering, you typically make a few calls to the LLM. And at each of the calls, you might change things about the input here to receive the appropriate output. This was one example. There's several ways that you could structure your system prompt to either impact the reasoning process itself or provide greater specificity about how the steps are articulated, formatted, and so on. Okay. So let's look at another one of the design patterns, which is the tool using agent pattern. And this is the case where an agent leverages external tools or APIs to enhance its capabilities. So you have your environment out here. This might be a query from a user. This agent receives a query like, hey, tell me what the temperature is in, I don't know, Nova Scotia, the average temperature in Nova Scotia today. And then this agent doesn't know that from its pre-training data, right? The LLM doesn't know what the temperature is today because it's not seen that when it was trained. So it's smart enough to know it doesn't know that. And it calls an API, maybe something from the Weather Channel or some other tool, gets the result and integrates a combination of the result of the API plus what it knows internally in order to respond back to the user. Okay. One example of this that is actually pretty common is to use the calculator API to solve math problems. And the reason this is common is because large language models are not, built to do mathematics. They're built for linguistic or rather probabilistic reasoning in the inductive sense over words. They're not really meant to do um, formal symbolic reasoning in the mathematical sense. So the advantages of using this tool using agent pattern is that I would argue that it's actually essential for real world applications. If you want to build any kind of system that's going to touch users, you will probably have to integrate at least one tool into that system. It's also, if you design it correctly, very modular and extensible because you can make this agent here aware of a set of tools in the system prompt that it can call. And as you add more tools, you can update the system prompt to make the agent aware of those new tools. And so it's therefore modular, it's extensible, it's flexible. And for this reason, this is a really common and useful agent design pattern. The limitations are, of course, that you have to have a system in place for error handling when the tools fail. These APIs, some of them might be under your control. It could be a database that you own, but some of them may not be. It might be a third-party API that you call from the Weather Channel. And if that fails, you need a way for the agent to be aware of the failure and either go to a backup tool or respond back to the user that, hey, I couldn't respond because there was an error. There's also, depending on what the user passes here, there might be some security considerations when you're considering calling external tools. For example, if a user here accidentally passes their credit card number forward, you may not want to go pop that credit card number and other information into a Google search or some other place that would retain a public record of it, as an example. Okay, so that's the tool use pattern. Let's go through a real example, just like we did previously, to help you develop your intuitions for how you would implement the tool use agent in practice. So you'd start with a system prompt, and it might look something like this. Your tool using agent, your available tools are, and then you'd list them. So maybe we have a calculator API, and we have the post request, as well as what's expected in the body of the post request to this API, as well as how we want the result to be returned. And then maybe we have something similar for the weather API. We have an example API endpoint here. We have, in this case, a GET request that it requires, and we specify again the response format. We also specify down here some rules. We want the output to be JSON. If it's a question that involves math, which obviously the agent will have to assess, then we want to call the calculator. If it's a question about the weather, we want to call the weather API. And when calling the tool, we want to return Python code as a string that we can execute. And finally, if we're passed a JSON with a tool result, we want to forward that back to the user. That's because we've got a loop here, right? The user is going to ask a question. The agent is going to call some tools. And then those tools are going to respond with results. And we don't want to just get stuck in this loop. We want to be able to pass those forward to the human being. So with the system prompt specified, the first step might be for the LLM to choose the right tool given the user input. So let's say the user input is, what is 5 plus 2? Well, what we'd expect, given the way we wrote our system prompt, where it had the weather API and the calculator to choose from, is that it might return an output that looks something like this. You might notice it's JSON formatted as we specified, and it says, hey, you need to call this Python code, import requests, response equals request.post. Here's that API endpoint, and it passed in the JSON expression in the format that we had specified within the system prompt. And it prints, let's say, the response that's returned. Of course, after the agent does that, we have to, using the system now, call that Python code. So let's say that the system in this case is a Python environment. We'd run exec and we would execute exactly the string that we were provided by the large language model. We would get a result from the tool. Let's say the result is hopefully 10 if it's a calculator API. And then we'd pass that result back to the LLM. So the task was, what was the tool? The tool result was 10. And this informs what we return back to the user, 10. Okay, so that's a concrete example of a tool use pattern. A memory augmented, or what's sometimes synonymously called a retrieval augmented pattern, is, I think of it as an extension of this tool use agent, where one of the tools that you have down here is a database or some other storage of information that's relevant for generating your response. An example of an agent that might need to use this is something that navigates the web, let's say to Domino's.com, and orders your favorite pizza. Why? Because in order to make the order, it has to remember first what your favorite pizza is. It would then also have to be able to take your credit card information, put it in the appropriate place, put your address, and so on. So it needs some memories about you, right? It needs to be able to not only have those memories about you, but to be able to retrieve the memories as a function of, let's say, what the web page contents look like. Okay, so memory augmented or retrieval augmented patterns are also really common when you're building real world applications where you need personalization, the ability to learn and adapt over time. You want to reduce mistakes. Of course, there are some unique challenges that come with these memory augmented systems. The first is that you have to deal with how you fetch from this memory. Later lectures, we're going to be talking about some of those retrieval strategies. Like if you have a database of contents, you want to pull from that database to surface the most relevant information to the agent. How do you do that? That's content we're going to be covering later in the semester. But suffice it to say, you have to handle this when you're doing a retrieval augmented pattern. And what comes with that is the risk of pulling the wrong information, pulling outdated information, or again, surfacing information to this external tool, in the case of the pizza ordering agent, that places you at a security risk. Maybe you give a social security number instead of a credit card, as an example. Okay, another one of these patterns is the React pattern. And this is really a combination of two of the patterns we've seen previously. In fact, even the previous one was just an extension of the tool calling pattern that we saw, which is why I didn't take you through a specific example. In the case of the React pattern, the agent is alternating between taking reasoning steps and taking actions, often using tools or APIs. So you already saw chain of thought, that's the reasoning. And the difference between the React pattern and chain of thought is that at the end of a sequence of reasoning steps, you have an action step. And that action step could be calling a tool. It could be responding. It could be accessing a memory. And doing this in series, right? Either reasoning followed by action multiple times up until a point of termination, or at its simplest, just one reasoning followed by an action loop that results in your final answer. A common example use case here is reasoning about a question, querying a database, reasoning again, calling a tool, and doing that in a pattern until you can answer a user question. Really important for complex multi-step tasks. A lot of the more performant general purpose AI systems that people are building actually use this React pattern. The limitations, of course, are exactly what you'd expect. It's more complex, and what comes with the complexity is additional overheads. In this case, there is a state management problem that you have to recall. So if you're performing a multi-step reasoning and action task, and that lasts for a while, you may recall when we did the chain of thought that each time we were passing the previous state forward into the next stage of the reasoning process. Well, you could imagine that if this gets very long or complex, that the input side after a few steps could get quite long. And as we discussed in the first lecture, if you pass too much information that's irrelevant to an LLM on the input side, you end up hurting your responses. So you have to take care of things like state management, figuring out how you store the intermediary results after each reasoning step, the consequences of the action, and surfacing the subset of those steps and the actions that are relevant for the next steps and next actions you have to take. So there's these additional overheads. That results, of course, in additional needs for robust error handling and some cost to the speed, understandably. The human in the loop pattern is actually a very simple extension, typically of the React pattern, where you have an agent that's performing the reasoning and it's taking an action, but that prior to taking that action, which is now moved over here, compared to the previous slide where it was here, it's now jumped over here. In this case, after the reasoning step is complete, you ask a human to verify, either decline and kind of go back to square one, or approve so that the action can be taken. Okay, this might be a design pattern if you had a tool that you wanted to extract findings from clinical notes, for example, that were going to be used to schedule follow-ups with patients' CT scans or whatever. This helps ensure that all actions taken by the system are validated, which is great. You can also configure this so that you bypass human verification when the confidence is high. You may recall from our prompt engineering lecture that there are some very simple techniques and also some more advanced ones that will help you assess how confident an LLM is in its response. The simplest of those is to just ask it the same question 5, 6 times and see if it changes its response or if it's very consistent. So you could imagine a situation here where you pass information in the reasoning process. You go through that reasoning process 3, 4 times. If there's a contradiction somewhere in the outcomes of the reasoning, then you have a human step in to adjudicate basically the differences. Okay. The third advantage of this is that when you combine this with proper memory management, you can actually enable an agent to learn from its mistakes. So imagine we have a loop here where the agent proposes a reasoning path, a human declines, but then we store that declining of the proposed action and we store it within the agent. And then we have the agent learn from that as a memory the next time it generates its reasoning path. As, for example, in a few shot sense, we inject this as an example of the wrong reasoning path. That would make sure that the next time we encounter a similar problem, we're more likely to achieve the approval. Okay. The limitations of this, of course, are every time we add a new block to a diagram like this, we're adding additional steps that require debugging. In the case of the unique challenges that exist with human verification, if you don't have enough that sort of flows through this system automatically, without the human needing to look at it, you risk the system being seen as redundant. That is, this human could say, well, if I'm going to have to approve everything and look at everything anyway, why don't I just look at the input directly? Why do I need your AI agent? And so thinking through basically what you pass to the human and what you bypass is very important for this kind of AI agent pattern. A last thing to note here is that Human beings also make mistakes, and so you you might have a circumstance, depending on how reliable the human user is here, where even if they decline an action, it may or may not mean that the action was the wrong one. So there's sort of an interesting meta problem to be solved when you're dealing with human in the loop. Okay, the last of these that I want to cover is the agent orchestration pattern. This one's actually very easy, I think, to understand, and it's related to what you're doing in your first homework assignment for this class. This is where you have one agent called an orchestrator, and the agent can basically call a bunch of simpler kind of prefabbed, pre-specified agents here. And this orchestrator can figure out how it wants to call these agents in sequence. One of those agents could be a human, by the way, to orchestrate the responses across the set in order to aggregate and return the results back to the user. This is actually pretty good. It's a simple pattern and it's pretty good at handling complex multi-step tasks, I think, for the level of complexity. Depending on how you design it, you can also get really nice parallelism out of this task. So if you have, for example, a task where you need three things to happen in parallel and you've designed your agents appropriately, you can distribute the tasks outward, collect the results, and aggregate in the orchestrator in less time than sequentially putting them through. Of course, the main challenge of this approach is you need this orchestrator to either be prompt tuned, fine tuned, or be provided with really high quality few shot examples for how it does the orchestration of these agents to get high quality results here. As part of that, you may end up dealing with more complex state management problems in a design pattern like this. So now that we've covered the motivation for these design patterns in AI agents, and we've also gone over some of the basic or essential design patterns that are used today, let's shift our attention to some of the emerging tools and methods that we're seeing in the scientific literature. The source that we're going to be using for the coverage today is the archive paper that you see linked here. The primary goal of that archive paper was to cover a review of prompt engineering methods, but they have a really wonderful section, I think it's section 4 in the paper, that covers some agents that they reviewed, which have had an impact. They've been highly cited by the community or have been widely used to inform secondary activities that are under development in the research community. So the four groups in the taxonomy that were provided in the paper were tool use agents, code-based agents, observation-based agents, and retrieval augmented generation agents. And you can see on the right-hand side here a set of the tools that are covered within the paper. I do encourage you to go read through all of those. For the sake of our lecture today, I just want to highlight 4 of these, specifically the 4 that I'm showing here on the furthest right, so that you have an idea of some of the more innovative approaches that people are taking for the design of agents that I suspect will be making their way into the next generation of AI agent design patterns. Let's start with the first one, MRKL systems, which stands for Modular Reasoning, Knowledge, and Language Systems. Specifically, I'd like to cover a really neat paper which disclosed a tool called Toolformer, which was trained to decide in a piece of text that was provided, so in a prompt, which API calls to make, when to call them, and what arguments to pass. And what I'm showing you here are 2 figures that come from the paper. On the left-hand side, I've got the first figure, which is showing some text that someone might put in a prompt. Let's say here we have the New England Journal of Medicine is a registered trademark of, then you can see there's this purple text, the MMS. So this purple text is actually what the Toolformer model is generating. You pass in the text up to this point, the New England Journal of Medicine is a registered trademark of, and Toolformer figures out that it can call an API on its own, just based on the text. It can call an API to answer this question about who owns the registered trademark of the New England Journal of Medicine. In this case, it calls the QA tool and it passes in this query and it gets the answer Massachusetts Medical Society, which you can see matches the actual answer in the text here that they're showing, the MMS. Another example here is out of the 1,400 participants, 400, or, and it's smart enough to understand that in order to answer this question, you need to call the calculator API and take 400 divided by 1,400, which yields 29. And as you can see in the actual text that they trained on, 29% was in fact the right answer. So this sort of very genius trick that they used to generate Toolformer was taking data sets very similar to what you see here, where a question implicitly was asked and the response was generated, and generating a data set where, as they stepped through this text, at key moments, they made a set of API calls to a collection of APIs that they have in the back, Wikisearch, Calculator, and so on. And then they figured out how close basically was the response of the API to the authoritative text that we trained on. Okay, so how close was the response Massachusetts Medical Society to the MMS? And the idea is that if the API generates a response that's very close to the MMS, or in the case of the second example, if the API generates a response that's very close to 29%, then we know that for a question that looks like this in the text, that the right thing to do is to insert an API response here. This is useful from a training perspective because now we can ask any open question, and Toolformer gives us a way to suggest which API calls to make to answer the question that we're interested in. So a really neat idea. Their GitHub repository was starred over 2,000 times. Definitely suggest you take a look at it and read the full paper if you're a graduate student in this course. A phenomenal take, I think, on self-supervised development of a transformer that not only knows how to generate the next token, but also knows when to call a tool to help it answer a question. Okay, so we've covered the first of these systems. Let's move to the second one. Program-aided language modeling. Now this one is so straightforward that it won't even take me much time to cover. And in fact, we covered sort of a rendition of this when we went over the prompt engineering lecture. There's a paper that was published where they described this program-aided language model. And the idea, very simply, was to take any input that a user gives and to train the system on how you translate this input into code. So in the case of this example, Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have? The idea is to turn this input into a series of Python commands that could be used to compute the answer, and then to simply execute the Python command as they're showing here on the output. Okay, so very straightforward, very simple idea. Procedurally, how you do this is by asking a language model to determine perhaps if this kind of task or question that's being asked by your user is better suited for deductive reasoning or symbolic reasoning, and to, if the answer to that question is yes in your chain of thought, to resort to casting the problem to a programmatic form, Python, for example, and executing the code so that you can perform the symbolic reasoning more effectively. Okay, so that's an example of program-aided language models. Let's move to the third example of lifelong learning agents, specifically Voyager. Now, this paper I actually thought it was a fun example because it does a deviation away from text and is thinking about an AI agent that exists in the context of the game Minecraft. And specifically, what this agent is trying to do is propose exploratory tasks to take or actions to do in the context of Minecraft, execute those tasks, save the consequences that led to a good outcome as memory. How does it do this? Well, it starts by defining basically some of the things that the agent should try to achieve. It should mine wood, it should craft a table, it should combat zombies, and eventually it should mine for diamonds. So it's sort of given some guidance that it needs to do these things. As it's trying to progress through this sequence in order to get ultimately to the point of mining diamonds in the game, um, it can propose exploratory tasks that it can take, and in this case, it's the form of code that can be executed as actions in the game so that you can attack the zombie as an example. And then it checks how well it was able to proceed through this, this set. Did it progress basically? Did it defeat the zombie? Did it effectively create the crafting table? Did it increase its inventory of wood and so on? And as the actions that it takes succeed and or fail, it will update the its memory of certain actions as skills that it stores in a skill library. And this skill library can be used to either pull the best skill for a task, or you can explore, in an exploratory sense, propose new tasks that you learn from when you're interacting with the world. So the key idea of Voyager, which I thought was really cool, is the proposing of new exploratory tasks, executing them, and saving the consequences as memories, so that the agent isn't just responding to the environment, but the agent is trying to actively explore the environment as well. And this was done in the context of Minecraft, but you could anticipate this could be done in other ecosystems as well. Okay, let's come to the last one here, which is iterative retrieval augmentation. This is based on a paper where they described a method called FLAIR, where they iteratively predict upcoming sentences, and if they were uncertain about one of the tokens in those sentences, they queried for an answer. So I need to start by motivating why I think this is interesting. When you're dealing with a memory or a retrieval augmented generation system, so that's where you have the agent and it calls a database to collect information, you always have this devilish problem of when do you call the database? Basically, when do you phone the friend? When do you go to the memory bank and try to pull it? And so the innovation in this paper, which I really liked, was they came up with a principled way to determine when you should call the database. And it works sort of like this. They have an input, let's say generate a summary about Joe Biden, and then they can have their language model generate an output. Joe Biden was born on November 20th, 1942, and is the 46th president of the United States. Okay, these are their examples, not mine. What you do after this is if all of the tokens in this sequence, the LLM was very confident about, and you can measure this by using the logits, which are the probabilities of the token given all the previous tokens in the sequence, then you accept this sentence. You can see it says, hey, this looks like it's pretty likely, so I'm going to move forward. Let's say that the next sentence that it wants to generate in the summary is Joe Biden attended the University of Pennsylvania, where he earned a law degree. But these two parts of the sequence, University of Pennsylvania and law degree, it's less certain about those two. So the logits associated with the sequence of tokens that generate these is low. Then this becomes the triggering event where, as you can see on the figure on the right-hand side here, a search query is performed against some database, some tool that returns the correct university. In this case, University of Delaware, and in the case of the law degree, Bachelor of Arts in History and Political Science. Okay, so very simple idea, but very elegant too. Try to figure out every time the LLM is generating a portion of its response, where it was confident and where it was less confident. In the places where it was not confident, you want to go do a retrieval of information from an authoritative source, a database, a tool, and so on. In the places where it was confident, you can let it operate. That's it for today's lecture. See you in the next video.